This video focuses on group workday alcohols. In the first step, we're asked to draw the product of the reaction of this conjugated carbonyl with sodium borohydride. It's always good to draw your reagents to help remind you of how they work. Here we've got a negative charge on boron, so we know that we've got a source of electrons, and our sink of electrons is going to be this carbonyl carbon, because we've got an oxygen carbon dipole where the dipole is pointed toward the oxygen, which gives the carbon atom a partial positive charge. Now, the reason for the methanol in this reaction is to provide a proton source. So the second step in our reaction mechanism is to protonate our alcohol. And we get this product. Sodium borohydride does not react with the alkene, so this alkene stays intact. And that gives us B as our answer. Number 2, predict the best set of reagents that will accomplish the following transformation. We're going from an alcohol to a carboxylic acid. Now this is a matter of memory, looking at your oxidizing agents and remembering which ones will go to stop at an aldehyde and which ones will go to a ketone. Answer B goes to the aldehyde. And the oxidizing agent we want here is sodium dichromate. And also number D goes to the aldehyde. Now we want to go to number 3, where we get a mechanism that goes to our product. I'm going to start far over on the left here, so we've got plenty of room. When we look at our reagents, we have a dipole going from magnesium to ethyl group, which means that the bond between magnesium and the ethyl group is our nucleophile. And our nucleophile attacks the carbonyl carbon because that is our electrophile. We've got to install the ethyl group. And then in our next step, the carbonyl oxygen electrons come down to reform the carbon oxygen double bond, and we kick out methoxide, even though it's a poor leaving group, because we can kick out epoxides when we're working with esters. That gives us a ketone product and the alkoxide. And here you want to ask yourself, are you going to protonate that alkoxide? And the answer is no, because you have not yet introduced the water. And this should have been written with an excess there for that Grignard reagent. And the Grignard reagent is going to come back and it will attack the carbonyl carbon again. You need to install the new ethyl group. And now we can add water in our second step. And it doesn't matter which one of these alcohols you protonate first. And now we have our product. The next question wants us to transform an alkene into an aldehyde. So here we know there are no new carbons. We've got 5 carbons in both examples. And what we need to do is form an intermediate that has an oxygen atom in it. And that intermediate is going to be this alcohol. So we want to oxidize that alcohol to form a carbonyl. But first we need to add water across the pi bond. And to add water across the pi bond, notice that we are working with the less substituted carbon atom. So we need to introduce reagents via a hydroboration oxidation. Then when we think about what reagents do we need to accomplish this oxidation, we want to use our less oxidizing reagents, our gentler oxidizing reagents. So one example that we could use here is pyridinium chlorochromate and dichloromethane. Now we have to draw an NMR spectrum of the product, and I'm going to draw this molecule larger and add all of the protons to this molecule. Next, what I want to do is ask which of the protons are the same as each other. We've got 2 methyl groups on this molecule, but let's see, I left out a carbon atom there. But these 2 methyl groups are not the same as each other. Every proton within each methyl group is the same. So this shows us that we've got 5 different signals for our proton NMR spectrum, and we want to think about which one is going to be farthest to the left and which one's going to be farthest to the right. And our spectrum is going to have the gray proton farthest to the left because it's the closest to the carbonyl. The next one's going to be the yellow proton because it's next closest to the carbonyl. Then the red and the green are about the same distance from the carbonyl, so they're going to show up closer together, and we actually don't know which one's going to be to the left or the right. We would have to take that measurement and see. But the blue are the farthest away, so they're going to be even more downfield. Then we want to ask ourselves how many carbons, how many protons does each type of carbon have? This shows us what to do for our integration. So down at the far left in the gray proton, we've got a signal that's going to integrate to 1, and it doesn't have any splitting because it's not next to a carbon with a proton neighbor. So next we've got our yellow protons. They also integrate to 1 total, and we're going to ask ourselves, how many neighbors does that proton have? And we've got our red neighbors and our green neighbors. So there are 5 neighbors total. And remember that we add 1 to the number of neighbors to get the splitting pattern. So let's put that around 4 ppm. So we're putting down a heptet with an integration of 1. Then for the green protons, or the pink protons, we want to ask ourselves, how many neighbors does this have? And we have 1, 2, 3, 4 neighbors. So that means we're going to get a pentet for the multiplicity of this peak. And this peak is a little taller because we've got a multiplicity of, or we have an integration of 2. Now let's go to the green protons. The green protons have 1 neighbor, and that means that its multiplicity is going to be a doublet. With an integration of 3. And lastly, for our blue protons, we have 2 neighbors, the 2 pink hydrogens. So that's going to give us a multiplicity of a triplet. Triplet with an integration of 3. So let's go on to the next one. This is a pretty long problem. We want to transform this phenyl bromide into a compound with 3 new carbons and an alkene. And so what we want to do at some point here is change this molecule into a Grignard and have that attack an aldehyde so that we can then have 3 new carbon atoms that are installed on that phenyl ring. But what we know is that if we want to make the Grignard of this molecule in the presence of an alcohol, that won't work, that the alcohol will react with the Grignard reagent. So this is not a compatible reaction. So instead of an alcohol, what we need to have is a protected alcohol. And that can go on to react with the aldehyde, and what we can do next is go directly to the product with concentrated sulfuric acid, because concentrated sulfuric acid will allow for an E1 elimination of this alcohol and a deprotection of the TMS group. Now, if we want a slightly higher yield, we can turn that alcohol into a tosylate, and then, oh, let's see, that's not right. Here. And now we want a strong base to undergo an E2 reaction. And then we can use acidic conditions or tetrabutyl ammonium fluoride to deprotect that alcohol. Now we've left out a step in the beginning, which was how to get to, we've left out two steps. How to get to this molecule, our key intermediate. First, we need to install our protecting group with TMS chloride and triethylamine. And then we want to make our Grignard reagent by treating that compound with magnesium. Well, that is all for this video. I hope you found the exercise helpful.